Today we're going to take a look at the principle of conservation of mechanical energy and just review a couple of concepts about it real quickly. This will approximately correspond to homework Work and Energy Part 2, questions 12 through 16. Again, I say approximately because we're just going to review some principles. We're not actually going to work that problem exactly. That problem refers to a particle which is on the side of what's described as a smooth hemispherical bowl. Rather than try to draw a hemisphere, I've just drawn a circle. So there's a lovely diagram on your homework if you really want that to look like a hemisphere. Anyway, so here we have a smooth hemispherical bowl. Smooth is code for completely lacking in friction. So that means that as this particle is sliding back and forth along this magical half pipe of a bowl, it will in fact be obeying the law of conservation of mechanical energy because there's no friction acting on it. Remember, that's the big criteria, that's the big condition for the law of mechanical energy to apply, and that is that there be no friction. Remember that if there's no friction and so the law of conservation of mechanical energy applies, then that means the mechanical energy at any one point is equal to the mechanical energy at any other point of your choosing. And this question actually asks for the mechanical energy of the object at 3 points, at point A, point B, and then point C, which interestingly enough is not quite back up as high as A. And so here we have point A, point B, and point C at a slightly reduced height. And the mechanical energy, which of course is made up of gravitational potential energy, elastic potential energy, and kinetic energy, and then that's equal to those same three quantities at any other point. So GPE2 plus EP E2 plus KE2. All right, now in this case, there's nothing providing elastic potential energy. There's no bungee cords, there's no rubber bands, there's no springs. And so really we could just as easily have left elastic potential out of this and said, well, the GPE and the KE at any one point is equal to the GPE and the KE at any other point. Okay, and so that'll be the basic principle that we'll be working with. Again, this set of equations, or this set of ideas here, began all the way up here with the idea that mechanical energy is conserved. So you really should start problems like this by stating this idea, just to demonstrate to your grader that you do understand what you're talking about, and you know that this is legitimate because mechanical energy is what's being conserved. All right. So at this point, we've got the object, and it's going to be sliding down. And let's just say that the question says, what's the gravitational potential energy at this point? All right. Well, we can see that point A is level with the center of the bowl, and so it turns out that its height then is actually equal to its radius. If we were to look here and we see that its radius, covers this distance, well, then that'll be the same, that radius which is given to you in the question. Well, then that's, if you were to swing that on around the circle to here, we could see that that would be equal to the height above the bottom of the bowl. So if it asks for the GPE of A relative to B, well, the GPE at any point is equal to m times g times its height relative to some reference. And in this case, you're given mass in your question. and we understand g is 9.8 or 9.81 meters per second squared. In this case, height is actually equal to the radius of the bowl, and that also is a given quantity. So at this point, you have all three of those, and you would be able to solve for the gravitational potential energy at A. All right, well, fabulous. Now, if we take point 1 to be A, well, then we know GPE at A, it's some known number. And it turns out that since it's at rest here before it's released, the kinetic energy is actually 0 at point A. So again, if we treat point 1 as point A, then we can find our GPE, and when kinetic energy is 0. And so at that point, the GPE at point A is actually equal to the mechanical energy at every other point along the trip. So it starts off with a lot of GPE, and then as it falls, that converts and changes into kinetic energy as it gains speed. Well, then by the time it reaches the bottom of the track, it's at height B. And so the height is essentially 0. It is 0 at that point. And so GPE at point B, let's just finish this and look at GPE at point B. So then if we were to say, well, what about point B? Well, then GPE at point B plus the kinetic energy at point B. All right. And if GPE at point B, since the height is 0, then that makes the gravitational potential energy 0. Then we find that whatever the gravitational potential energy was at A, well, that's also then the kinetic energy at B. Again, you don't want to start out just writing that down, though. You want to begin with the conservation of mechanical energy and then work through that gradually, substituting zeros, again, just to demonstrate that you understand what's going on as the object slides around. So sure enough, then at that point, since this is a known value for you, you've calculated it here, that's equal to the kinetic energy at B. So now you can list that as the kinetic energy for B, or if you were asked for the velocity, you could go ahead and solve for the velocity, since the kinetic energy can be found from 1/2 times the mass times the velocity squared. And so at that point, again, you have mass, so you could, this is a known value, this is a known value, and you could solve for the velocity if you were asked for that. All right, well, now what happens to it is it slides on around the bowl and begins up the other side. Well, since there's no friction, it would actually end up at the same height that it had originally, straight across there. However, we're not interested in that height. We're interested in it when it's at a slightly lower point. Again, if you were to sort of erase all this in the box, or just start at this point again, and let's just pick up here. But now let's consider, rather than considering point B, let's consider position 2 as point C. All right. And so once again, we see that the GPE at point 1, or at point A, plus the kinetic energy at point A equals GPE at point C plus kinetic energy at C. Again, GPE at point A is a known value, and kinetic energy at point A is 0. So the GPE at point A is then equal to the GPE at point C and the kinetic energy at point C. Well, if we knew the height of the object at point C, we could actually then solve for its. We could actually find its gravitational potential energy. And it turns out that we do. That's a listed value. In my case, it lists that as 2/3 r. So I'll take r and just multiply by 2/3, and that will tell me what to put in this case. And don't forget the kinetic energy is still a part of the equation as well. So now this is a known number from our original calculation. This is now a known number since we just found that. And then we could subtract this gravitational potential energy from both sides of the equation and get a value for the kinetic energy. That could then be used either to know the kinetic energy itself, just in total, or set the kinetic energy, once you know its value, equal to 1/2 times mass times the velocity of point C squared. And you could then, knowing the mass, find the velocity at point C. So with just a little bit of understanding, that is the idea that it's frictionless, so mechanical energy is conserved, the idea that we know the radius here, the height, and the mass of the particle, we can actually find gravitational potential energies and speeds and kinetic energies at all points around the hemispherical bowl. All right. So again, just kind of take a look through that and review it again if you need to. I hope that was helpful, and thank you for watching.